Okay, welcome back to my course in probability theory. So in the last class, we have given you the concept of an event, basically, and it's some of its special types like certain event, impossible event, and mutually exclusive events. So I hope that concept is clear to all of you. Now today class, actually I'll be discussing with another very important concept, which is called event space, or sometimes also known by the name sample space. So what is an event space or a sample space, as we call it? Basically, in one line I can say that event space or sample space is a set of all possible outcomes or event points of a random experiments, right? As we have discussed the concept of random experiment in the 2 classes back, I told you that a random experiment has possible outcomes, right? So if you collect all possible outcomes of a random experiment, that collection is called a set, right? And that set is nothing but a sample space. Like in the experiment of tossing a coin, my sample space will comprise of head and tail. In the experiment of rolling a die, my sample space will comprise of 1, 2, 3, 4, 5, 6. So we just write just like we write in the concept of in set theory in the tabular form, of representing a set, that is writing the elements of the set separated by commas, and that's so what we do actually in case of a sample space. So sample space is actually denoted by the symbol capital S, that's standard symbol that we use in mathematical theory of probability. So that is important point. And the example that I've taken over here, you see that the experiment is being taken as rolling a die, and there I have written the sample space of the experiment of rolling a die, which is 1, 2, 3, 4, 5, 6, right? So, so this is the sample space of the experiment of rolling a die, because there are 6 possible outcomes. So I have taken all the possible outcomes, and it forms a set. And that set is nothing but a sample. So a sample space is nothing but a set. It's basically a set, okay? Because you see the outcomes are all distinct and they are well defined, so it forms under the classification of set. So I told you that I may use the concept of set theory now, because set theory is one of the prerequisites to learn this course. So now on I may be using the concept of set theory to discuss further. So we find that a sample space is nothing but a set, which is the collection of all possible outcomes of a random experiment, right? Now this elements that I have taken to define the sample space, which are 1, 2, 3, 4, 5, 6, which are actually the outcomes of the random experiment, are called event points. So we will not use the term outcomes from now on, we will be rather using the term event points from now on. These are called event points of the experiment E of rolling a die, right? Now let us now define 2 sets, right? So we have a set S comprises of the 6 possible outcomes, which is a sample space of the experiment of rolling a die, and under the context of that we have defined 2 sets. One is the set A, 1, 3 and 5, and the other one is set B, which is 3 and 6. Now you can see from the basic concept of set theory that clearly A is a proper subset of S and B is also a proper subset of S. That means both A and B are actually contained in S. Now when both A and B are contained in S, okay, what happens is that it actually comes out to be nothing but events connected with the experiment T. Because you see the set that A I have taken, it comprises of 3 outcomes, 1, 3 and 5. Out of the 6 outcomes, only 3 of the outcomes are actually favoring the event A, and 2 outcomes, which are 3 and 6, are actually favoring the event B. So that means they are actually proper subset of S, but they are actually what? They are nothing but events, because you see 1, 3 and 5 will comprise the event odd phase, and 3 and 6 will comprise the event multiple of 3. So that means any subset, okay, if we consider of the sample space S, will happen to be an event connected with that experiment E, whose sample space is S. Like here, we have taken the sample space to be of the experiment of rolling a die, and we have taken two sets A and B under the context of rolling a die, and we have found both A and B are contained in S, and as a result both A and B are events connected with the experiment E of rolling a die, right? So that's the conclusion we draw. It's a very important line, that thus any subset of S will be called an event connected with E. Any subset of S. Okay, so any subset of S, that is with the most important line, any subset of S will be called an event connected with E. Right, like here A and B are basically events connected with the experiment of rolling a die. Now, from this observation, we get several observations. Now, the first thing that we can say is that since A and B were sets, so we can say that any event is a set. That is very, very important. And that's why exactly why I use the concept of set theory in probability. Because any event in probability is classified or is said to be a set. Because you know a set is basically a, what is a set? Set is a collection of some well-defined distinct objects, right? So the sample space is basically well-defined and the outcomes are all distinct, so therefore it's a set, and any subset of the sample space is also a set, and that has been proved to be an event. So I can come to this conclusion, any event is a set. So whenever you're defining an event in the experiment of in the random experiment, you will see that that event is nothing but a set. It's a collection of some well-defined distinct objects. Now since any event is a set, now we go a bit of set theory. We just use the two simple properties of set theory to arrive at two very important conclusions. What we are doing is that we know from the concept of subset, we know that every set is a subset of itself. That we all very well know from the basic concept of set theory. That means the sample space is itself contained in the sample space. S is a subset of S. That means if S is a subset of S, then S must be an event under E, because that's what we told. Any subset of the sample space must be an event under the experiment E. Then what kind of event is S? Can you point out that or say that what kind of event is S? Because any subset of the sample space is said to be an event, so it must be an event under E. So that event is nothing but the certain event, because S is a certain event. Why? Since it contains all the outcomes of E. Because just now we told the sample space or the certain event are basically what? They are the outcomes of a random experiment, right? They are a set of all possible outcomes of random experiment. So a certain event consists of all possible outcomes of a random experiment that we have seen earlier in my previous class, and we can say then that the sample space is nothing but a certain event which as it contains all the possible outcomes of a random experiment T. So the certain event is denoted by the symbol S, which we use to denote a sample space. Thus the sample space of any random experiment is the certain event of that experiment. That is the important line. So the sample space of any random experiment is the certain event of that experiment. So when you are defining the sample space of a random experiment, you see that that sample space is nothing but actually that is the certain event of that experiment, because it consists of all the possible outcomes of the random experiment. Now again, if we use the basic concept of set theory, that is in subset, we know that the void, phi is a Greek letter and it means null set or void set. You know what the void set is, all of you know, because you have gone through set theory to learn this course. And phi is actually empty set or a null set which has no elements at all, denoted by the Greek letter phi. And we all know from the basic concept of subset that phi is a proper subset of every set except itself, because every set is a subset of itself. So phi is a proper subset of S. So if phi is a proper subset of the sample space S, then phi must also be an event under E, isn't it not? Then phi must also be an event under E. So then what kind of event is phi? Again the question comes, then what kind of event is phi? It's very simple. Phi will be nothing but the impossible event. Why? Because phi does not contain any element, because phi has none of the outcomes of the sample space. That's why it's phi, because it is an empty set or a void set. So, and why it's an impossible event? Because impossible event does not have any of the outcomes corresponding to our random experiment. So therefore, phi is classified as an impossible event here. Okay, so the impossible event is denoted by the symbol phi. Just like a certain event is denoted by the symbol S, the impossible event is denoted with the symbol phi. So these are the notations that we use in mathematical theory of probability. Capital S is used to denote a certain event, and for impossible event we use the symbol phi to denote it. These are standard symbols that we use, and that is coming exactly from this concept of sample space, right? Now moving further, we come to another very important concept, concept of complementary event. That is very important because we must know this concept before we proceed further. Now complementary event, I'll be explaining it from the set theory's point of view, because just now I have told you any event is a set. So I will be using the concept of set theory to discuss this very important concept of complementary event as right. So what is an complementary event? Right, an event which consists in the negation of another event is called complementary event. I hope you have understood this. If you have not, then we go to one very simple example. Before we go that, there is another way that how it is denoted. First we write that it is denoted by a bar. If you say A is an event, then its complementary event will be denoted by a bar. We put a bar just on top of A to denote the complementary event of A. Right? Sometimes in some books they use prefix C, AC. Right? They use A prime. A lot of ways they use, but I normally use this bar symbol. Right? Now, how it is defined from the set theory's point of view, how this complementary event is defined. You see, from the set theory's point of view, in the set builder notation, I can define a bar equal to x such that x belongs to S and x does not belong to A. Now, what is the meaning of this? The meaning of this is that a complementary event of A will comprise of only those outcomes which belongs to the sample space but which does not belong to A. And from this concept, as you all know set theory, it is S minus A, the difference of two sets concept. So A bar is nothing but S minus A, that is the outcomes which are in the sample space but which does not belong to the event A. That's why it's called complementary. So a fine example of a complementary event will be, let's say I take the event A multiple of 3 under the experiment of rolling a die. I have taken the experiment of rolling a die, and there I have defined the event multiple of 3. The multiple of 3 comprises of 3 and 6, right? Then of course the complementary event of A will be A bar, which is not multiple of 3. So not multiple of 3 will comprise of 1, 2, 4 and 5. As you see, 1, 2, 4 and 5 are not multiple of 3 in the experiment of rolling a die. So of course, so you see this 1, 2, 3, 1, 2, 4, 5 are basically belonging to the sample space here, but it does not belong to the event A, because event A comprises of 3 and 6. So that set comprises of what is known as not multiple of 3, which we denote by the symbol A bar. So A bar here happens to be the complementary event of A, that is multiple of 3. So that is the way we denote a complement, like the complementary event of what phase is event phase. So there's so many examples that we just take the difference of S and A, you will get the outcomes of the complementary event, and hence you can define that complementary event accordingly, right? Now from this complementary event definition, that leads to two very important you can say observations, or you can say elementary results. Now what are the two results that we get? The two results we get, the first one you can easily make out. The complement of an event, that is A bar, then whole bar, that is a double bar is used. So what is that? That is, you are taking the complement of the event. So if you go by the definition, because A bar is S minus A, so A bar whole bar will be S minus A bar, right? And so then again you apply the definition of A bar, which is S minus A. So you get S minus A. So if we apply the associative law now, so you just associate S and minus S, which leads to phi, and this minus this becomes plus A. So you get phi plus A. Okay, and phi plus A is actually equal to A. So you get back the event A itself. So the complement of A, because 5 plus A will be equal to A, I have not written it, but it will be equal to A. So the thing is that you are getting back the event A itself. That's very much logical, because if you take the complement of let's say the multiple, not multiple of 3. So what you should get? You should get back the multiple of 3. Let's say if you take the complement of the even phase, you get odd phase. Then again if you take the complement of odd phase, you should get back the even phase. That's quite logical. So A bar whole bar must be equal to A, right? That is very much understood. Now secondly, you see that the sample space, and which we call it as a certain event, and the impossible event phi, they are complementary events of each other. Why? Because it's very easy. Because if you take the complement of S bar, by definition you will get S minus S, because from definition it is S minus S. In place of this S bar, we write S minus S, which is equal to phi, and phi bar is actually equal to S minus phi, right? So S minus phi, which happens to be equal to S. So that means S bar is phi and phi bar is equal to S, which means that the certain event and the impossible event are complementary events of each other. So they complement each other, right? So with that, I come to the end of today's class. I hope you have understood this concept of the sample space and the concept of this complementary event. In the next class, we'll come to one of the most important concept of probability, that is the sum and the product of 2 or more events. Okay, until then, goodbye, and we'll be coming back with that very important concept in the very next class. Thank you so much.